This video is going to be looking at topic 10D for the International IAS level chemistry from Edexcel, and we're going to be focusing on mass spectrometry and infrared. So we're going to be looking at how we interpret the data from mass spectra in order to suggest possible structures for organic compounds. So this is using our mass to charge ratio and also our fragmentation patterns. We're also going to be using infrared spectra in order to determine the functional groups that are present, or to be able to predict the infrared absorptions or give wave number data depending on what functional groups are present. So let's start off by looking at the mass spectrometry of organic molecules. So we've met mass spectrometry back in topic 2 when we were looking at simple diatomic molecules such as chlorine or bromine. Now we can actually use mass spectrometry to interpret much more complex structures. We're going to focus on some very simple organic structures, and we can figure out not only the molecular mass but also the actual structure itself. And now the mass spectrum of any compound is going to contain lots of different peaks, and this is due to fragmentation. And what that means is we're getting the compound breaking down into specific ions that have a positive charge, and the mass spectrometer will figure out what mass they have and a peak will come out on the spectra. So the peak with the highest mass to charge ratio, or MZ value, is known as the molecular ion peak. Now this peak represents the relative molecular mass of the organic molecule. So it basically means that if you have a molecule that has a mass of 56, you're going to have a peak at 56, and it should be the highest MZ value. There should be nothing else after that. Please note that this is different from the tallest peak. The tallest peak in the spectra is known as the base peak. So it is important that we do distinguish between these two things, especially when you are answering a question. If it asks what one represents the molecular mass, you need to be saying the highest mass to charge ratio, not the tallest. So fragmentation patterns are commonly used to determine the molecular structure of an organic molecule. And what actually happens with these fragments is they are formed when we get carbon-to-carbon bonds in the molecule being broken, and we form a positive ion and a neutral species, which is usually like a free radical. So if we look at the example here, we've got CH3CH3. We're going to break this bond here, and we're going to be left with a CH3 ion and a CH3 free radical. If we have a longer chain, you can see that we can get different fragments. We can get possibly a CH3 plus or a CH2 CH3 plus. And each of these fragments is going to have a different mass, and the mass will correspond to the MZ peaks in the spectrum. Remember that Z is your charge, and in this case the charge is 1. So it would be the mass divided by 1, and that's where we would see our peak. So let's have a look at an example. If we have a mass spectra of butane, now if you can't remember, butane is a 4-membered hydrocarbon. It is an alkane, completely saturated with hydrogens all around the carbons. So we have C4H10. Now what happens in here, as we've said, we get this fragmentation pattern, and that causes us to get some breakage between our carbon-to-carbon bonds. And when that happens, then we make a couple of different peaks. Now you can see that we do have some that are present, but we haven't labelled them. We're only going to be labelling the most common peaks. So they tend to be the ones that are the highest. So we've got a peak at 15, a peak at 29, a peak at 43, and a peak at 58. This one here, because it has the highest mass to charge ratio, this is our molecular ion peak. This tells us that the molecule has a molecular mass of 58. This one here at 43, this is our base peak, and it just means that this is the most abundant or most common fragment pattern. So one of the most common fragments that we'll see is with a mass of 15, and that is a CH3 or a methyl fragment. We can then have an ethyl at 29 or a propyl at 43. And of course, the butane with its positive charge is going to be our molecular ion peak. So you can see that these line up with the main peaks here. So when we're analysing a mass spectrum, there are a number of different key peaks that we're going to come across. The more you practice this, the more you will start to memorise some of these peaks. But I do recommend that you try to commit this to memory because it will become a lot quicker for you. And you'll see that it's the same peaks that come over and over. So we can have peaks like our methyl at 15. We can have a carbon-oxygen bond at 28. We can have an aldehyde group at 29 or carboxylic acid groups at 45. It just depends on the molecule itself. So let's have a look at an example. So compounds A and B have the molecular formula of C3H6O. Their mass spectra are both shown below, and we want to be able to deduce the structures. Now, when we have C3H6O, hopefully you realise that that can't be, obviously, a hydrocarbon. It also cannot be an alcohol because we don't have enough hydrogens. So we're going to have two possible answers here. We're either going to have propanal, which is the aldehyde, or we're going to have propanone, which is the ketone. And we want to determine from these structures which one is going to be which. Now, both mass spectra show a peak at 58. Now, this is our molecular iron peak, and because both of them are there, showing that same peak, that doesn't actually help us. They also both have a peak at 15, which means that we must have a CH3 fragment. Now again, because this appears on both of them, it does not help to distinguish the two structures. So what we actually need to look at is we need to look at the peak that is left. Now in A, we have a peak at 29, whereas in B, we have a peak at 43. Now, if we have a peak at 29, well, if we go back to our table, we said that 29 was either going to be a CH3CH2 or a CHO. Okay, so based on that, well, we know actually that we have both of those peaks because this must be propanal, because propanal is going to be drawn like this. And what we see here is we have this bond breaking and we end up with this fragment here and this fragment here, both of which are 29. So that must mean that A is propanal. Now we can confirm this by looking at the peaks for part B. So for structure B, we've got a peak at 43. And if we go back, we said that that could either be our peak that we see in a ketone, or it could be any of the other ones as well. Now, because these two here are not going to be produced by this particular molecule, this must be our CH3CO structure. So just to confirm, propanal is drawn like this. So we are seeing a fragment happening here, and this peak at 43 is going to be that part of the structure here. So part B must be propanone. So looking at the answer, you can see that it's telling us what we've just seen there, that the major peak at 29 must be our CHO positive or our CH3CH2. So this is the aldehyde propanal, whereas our peak at 43 is going to be our CH3CHO, because it cannot be either one of these, because they would also give in order to get that, you would have a radical being formed that doesn't show on our spectrum. So this must be propanone. Now, sometimes you may be asked to write the equations. Well, what happens is we've got our CH3CH2CHO here, so our aldehyde, fragmenting to form the ethyl fragment, and also fragmenting to form our CHO. And for our ketone, we have our CH3CO and our CH3 fragment being formed. So let's look at another example. This time we're going to be looking at C and D, and we're looking at these compounds that have the molecular formula C3H8O. Now that tells us that it must fall into our alcohol, so we've got two possible structures. We can either have propan 1-ol, which is our primary alcohol, or we could have propan 2-ol, which is our secondary alcohol. And we're going to use the mass spec to tell us which one is which. Now, of course, both of them have this peak at 60, which is our molecular ion peak, but again, that doesn't help us with the structure. They also both have a peak at 15, which we know is for a CH3 peak. So then we have to look at what is left over. So for C, we have a peak at 31, whereas for D, we have a peak at 45. So if we start with D, well, if we have our peak at 45 and our peak at 15, it is because we've had a breakage here, and we are then left over with a fragment that must add up to 45, and that is, we can see, from an oxygen, 2 carbons, and 5 hydrogens. So that must mean that D is propan 2-ol. Let's just check to see if C is actually propan 1-ol and how we can confirm it. Well, we look at this peak at 31, and this peak at 31 is caused when we take our fragment here between these 2 carbons, and we're left with 1 carbon, 1 oxygen, and 3 hydrogens, and that gives us a peak at 31. So that tells us that C must be propan 1-ol. So when we're trying to find out the structures, we want to look at what possible fragments could happen from our structures. So the best thing to do is to draw it out and then start to break the carbon-carbon bonds, and you simply just add the amount of mass for each of the fragments and we see if it matches up with the peaks that we have in our structure. So you can see that we've got the answers here, so confirming that in C, we have this 31, which tells us it was propan 1-ol, whereas D has the peak at 45, and it tells us that it is propan 2-ol. That's it for mass spec. If you want to practice that more, there are some questions that you can find on the internet, or you can check past papers to see if there are any specific questions. You may wish to check Unit 2 and Unit 3. So let's move on to infrared spectroscopy. Well, infrared is a type of radiation that has a frequency just below that of red light in the visible spectrum. So if our visible spectrum is here, this section here is our infrared. Now, when our molecules absorb infrared radiation, there are 2 possible effects that we can have. We can either have the bonds stretching, like this, so going back and forth, or we can have the bonds bending and moving like that. Now, in International A-level, we only consider the stretching vibration, so you don't need to worry about the bending. The amount of radiation that is going to be absorbed will depend on 3 things. It can depend on the length of the bond, the strength of the bond, and the mass of the atom involved in the bond. Now, because we've got these specific factors that do have an effect on the amount of radiation that is absorbed, we can then start to look at characteristic absorptions. So specific functional groups, because of the bonds that they have with their specific lengths, strengths, and atoms, they are going to have a very specific absorption, and we can use that to our advantage in this type of spectroscopy. The absorption of infrared radiation is linked to changes in polarity, so any small non-polar molecules are not going to absorb infrared radiation, so just please be aware of that. You do need to have a level of polarity. So IR spectra have a vertical axis, which you can see on the diagram here, and it is known as transmittance. And that is just another way of saying how much radiation has been absorbed. The horizontal axis is known as wave number, and it has a frequency with the unit centimetres to the -1. Now, what you must notice is that it goes in the opposite direction from what you would expect. It starts at 4,000 and it goes down to 500. And you can also see that we have a change in scale here. Now, don't worry too much about that. You're not going to be asked to explain why we do it like that. It's just to make you aware that there is a slight difference in the scale. So you need to take that into account when you're checking your peaks. Now, each of these peaks that I'm circling here will all be characteristic to the vibration of a specific group. So when the molecule is absorbing the infrared radiation, each of its functional groups will absorb a specific amount and it will cause a stretching vibration, and we will then see a peak on the spectra compared to that. So when we're looking at an infrared spectrum, we are interested in the intensity of each peak because it shows how much radiation has been absorbed. So if we have a weak intensity, it refers to a high transmittance value, and high intensities refer to a low transmittance value. So that just tells us how high or low the peak is going to be. We also, of course, need to know the wave number values. That is one of the most important things because that tells us which functional group it is. And we can also look to see if it is going to be a sharp peak or a broad peak. For example, if you look at the alcohols have a peak of wave numbers from 3750 to 3200. Now that is actually a very broad peak. And it's very wide. It can be very, very overpowering in an infrared spectrum. If we compare that to something like an aldehyde that has got its peak between 1740 and 1720, that would be a very sharp peak because it's a very small difference in wave numbers. So we should be able to do three things with infrared spectroscopy. We should be able to predict the absorptions that we would see in a spectrum based on the functional groups that are present. We should be able to deduce the functional groups that are present if we're given a list of wave numbers, and if we're given the wave number and the molecular formula, we can deduce a structure. So it all just depends on what you're given in the question, and that will also depend on how many marks the question is worth. There is a section known as the fingerprint region, which is between 1500 and 500 wave numbers, and these are results from bending vibrations, so we're not going to consider those in this course. You just need to be aware that they will exist, but we're only looking at any peaks that are above 1500 wave numbers. So this is a page taken from your data book. Of course, you all have a copy of your data book, and if you don't, you can find a copy of it on the Edexcel website. And you will have this in your exam, so you are not expected to memorise any of the wave numbers. So you'll be given this table in your data book, and you can use it to determine what the peaks are. Notice it does have the bending vibrations in for your CH, but as we said, these are going to be in the fingerprint region, so we're not actually interested in those. You'll be focusing on the stretching vibrations between all of the others. So let's look at a few worked examples. If we have the infrared spectrum of propanol, what would we expect to see? Well, propanol is going to be an aldehyde, so it's going to have this particular structure. So we should be seeing CH bonds absorptions, which will give us in the range of 2900 to 2820, and from 2775 to 2700. So again, you can check that on here. There's your aldehydes. And we will also have that very sharp carbonyl bond transmittance peak at between 1740 and 1720. So this is a way that we would be predicting the functional groups. If we had for worked example 2, if we're given the infrared spectrum of this particular molecule, what would we be seeing? Well, again, we can draw it out if we're not sure from the spectrum, from the structure. So this is going to be propan-2-ol, and the most common one that we're going to see, of course, yes, we will see the CH bonds, but the most common one is going to be this OH. And because it is an alcohol, we're going to predict a very broad absorption between those wave numbers. So it's important that we're distinguishing that for the aldehyde, as we said, this is going to be a sharp absorption, whereas for the alcohol, it is going to be a broad absorption. Worked example 3 gives us the wave numbers and then asks us to figure out which functional groups it contains. So we're going to have absorptions at 3,675, 2,870 and 1,735. So we would match each of these up to the data book and we would see that the 3,675 would be our alcohol, the 2,870 would be our CH bonds, and our 1,735 would be our aldehydes. This is simply just using your data book. So you must be comfortable with being able to flip through the data book and find the vibrations that are characteristic for each of these functional groups. So please make sure that the first time you see the data book is not when you go into your exam. Make sure that you're using it all during your past papers and you are familiar with what each page is and what each page has. If we look at worked example 4, so we have an organic compound that has absorptions in the wave number ranges of 3500 to 3300 and 3500 to 2500. So we want to again use our data book to help us with that, and now this is going to be an OH group, but this time it's not for an alcohol, it is an OH for a carboxylic acid. So you will see in the data book, if we go back, that our OHs, if it's an alcohol or a phenol, is going to be different to a carboxylic acid. So just make sure that you are picking the correct wave number range. And our absorptions between 3300 and 2500 are going to be for our amine group, and that could be for an amino acid. Now don't worry too much about knowing what amino acids are, because you haven't covered that yet. That is covered in year 13. But if that was going to be the answer, they would give you enough information. Probably in the question would be at the start saying this is the structure of an amino acid, showing that it has a carboxylic acid group and an amine group. So again, it's making sure that we read the question as closely as we can. If we look at worked example 5, we are this time looking to deduce the possible structure. So we're given wave number absorptions and we're also given C2H4O2. So we've got, looking at these particular structures, we know, or these particular wave numbers, we know that we have to have an aldehyde functional group and we have to have an alcohol functional group. Note that we cannot have it as ethanoic acid being our carboxylic acid because our range for our OH is out with that. So we've got 3450 and it's out with the range, so it can't possibly be a carboxylic acid. So our structure could only be an aldehyde group with a carbon that must have an OH group attached to it. Now, you've probably never seen this molecule before, but that does not matter. You can still work out its structure from all of the information that you are given. Worked example 6 is looking at an organic compound with the structure C3H6O2, and you can see that we're given the infrared spectrum this time as opposed to given the wave numbers, and we're asked to work out the possible structure. So we've got a couple of different things that we have to look at here. So we're going to have a peak here at 1700, and what we do have a peak here that is approximately 3000. And notice that it is not a particularly broad peak. So this is going to be for our OH, and because it's a thinner peak, then it must be a carboxylic acid, and this is going to be the carbonyl group of a carboxylic acid. So we go back up to our our molecular formula, C3H6O2. Well, if we're using our carboxylic acid group and we've got 3 carbons, the only thing that it can be is propanoic acid. Hopefully these worked examples are making sense, but let's have a look at a past paper question to give us some information about what type of question that we're going to see. So this is from the June 2018 paper, and we are given organic compounds that have been analysed using physical methods like mass spectrometry and infrared. Now, there are other parts of this question that are about chemical tests and quantitative measurements, but we're only going to focus on the spectroscopy. So we're given this mass spectrum, and we are also given this IR, and they've given some infrared data in the table, so you don't necessarily have to use your data book here. They are giving you a hand to figure out which one you need. So we want to know what can be deduced about ethanol from the presence of the peak at the mass to charge ratio of 46. So let's just go back here and let's see that this peak here is 46. So we already know that this is the molecular ion peak. And what does that tell us? Hopefully you can remember. It tells us the molecular mass. So it means that ethanol has an MR of 46, MR being your molar mass or your molecular mass. We want to identify the species that is responsible for the peak at 31 and the mass spectrum of ethanol, and we want to state how it's formed. So just to make this a little bit easier, let's draw out ethanol. So we have our 2 carbons, our OH group, and we're surrounded by our hydrogens. So we need to figure out a peak at 31. Well, we can only have one fragmentation of our CC bonds, so that must be this breakage here. And if we just go back, we can see that this is a very abundant peak at 31. So we can check that this side is going to be, well, 12, 13, 14, 15. If we fragment it here, whereas here we're going to have 12, 13, 14, 15, plus 16 is giving us a peak of 31. So that peak has to be our CH2OH, and always remember to put your plus sign. They will not accept any other answer. It cannot be written as CH3O because that is not the way that the molecule is actually made up. It is the actual fragment itself. And then for the second mark, it is how that is formed. Well, it's that we are losing a CH3. And that is due to the carbon-carbon bond breaking. You cannot simply just say that it is fragmentation. You have to say what is happening in the fragmentation. So we get this carbon-to-carbon bond breaking and we're losing that methyl. And that leaves us with the CH2OH+. And then part 3 is asking us to identify one feature of the infrared spectrum which confirms the functional group in ethanol. Well, our functional group that we're going to be looking at is going to be our OH. So if we go back, you can see that we have this lovely broad peak here, and we can check that it falls within our range of 3,200 to 3,720. Notice that it can't possibly be the carboxylic acid, of course, because that's not an ethanol, but just to check, it does not fit within the wave number range here. The carboxylic acid would fit somewhere into there. So we want to make sure that we're including the appropriate wave numbers, so it's going to be our OH group. And that gives us wave numbers between 3750 to 3200 centimetres to the -1. Well, hopefully that's made spectroscopy a little bit clearer for you. Again, if you do want to try out some more examples, there are plenty of IR questions that are available in past papers, or you can find some online, or even check the textbook. There are worked examples. There are also the checkpoint questions and the chapter questions. If you have any questions or anything that you're not sure about in this video, please leave a comment below, and I hope to see you back on the channel in future to check out what other videos we have.